A ballistic pendulum is a device that is used in physics labs to measure the momentum of a projectile. Our problem here is we have a 50-gram pellet fired into a suspended block of wood of mass 0.65 kilograms, and it remains embedded. So the bullet gets here, gets stuck in there. The pellet gets stuck in the block. That's a perfect inelastic collision. After the impact, the block swings up to a height h. The initial speed of the pellet is 20 meters per second. Typically, when you use these things, you're trying to find the initial velocity with this setup, but this time we're given the initial velocity. We'll find a bunch of other stuff. A, what is the initial momentum of the pellet? B, what is the kinetic energy of the pellet before the collision? Then find the velocity of the pellet block system, and we've actually circled that here, right after the collision. Some more parts. What is the kinetic energy of the pellet block system right after the collision, before it starts moving? What is the gravitational potential energy of the pellet block system when it reaches its maximum height h? And then find the maximum height h of the pellet block system. Before we start solving the problem, we have to tell you this part right here. Subscripts and superscripts will be key in this chapter. We have to distinguish between multiple objects that collide, an object's momentum and velocity before and after a collision, and two objects that undergo a perfect inelastic collision and stick together, becoming one system, one unit. Here are the key subscripts and superscripts we'll use here. P stands for pellet, B stands for block. The prime sign after something like velocity, that means after the collision. And then if we put P and B together, that stands for the pellet block system. What is the initial momentum of the pellet? And we started off fairly straightforward. P is equal to mv. The initial momentum is before the pellet strikes the block. So we have P is mv. P is equal to mv0. That's the initial velocity of the pellet. And you can see the P there. So we actually have two subscripts there. And then we put in 0.050 kilograms. Now we were given 50 grams. We work in kilograms. So over here is the unit conversion to go from grams, 50 grams, times 1 kilogram, which is equal to 1,000 grams. Grams cancel, and we get 0.050 kilograms. Do the math, and we have a momentum of 1 kilogram meters per second. And actually, these units here had a practical application years ago. You could find the velocity of a bullet by shooting it into a block and measuring how high up this was. Now, obviously, it's a lot more rigorous than the lab equipment we have, and we're kind of doing this one backwards. We're given the velocity, but it's nice to know the history of these things. What is the kinetic energy of the pellet before the collision? Have our kinetic energy equation here. That's the general one. And then we have mv0 squared pellet, plug in the numbers, and we get 10 joules. Find the velocity of the pellet block system right after the collision. We're going to assume no external forces here, as friction is not mentioned, so there is no impulse. Okay, and what is impulse? Impulse was defined as force times the time it's exerted over. So since our impulse is 0, and we have our impulse momentum equation, where impulse is the change in momentum. Impulse is 0. 0 equals final momentum minus initial. So P0 is equal to PF. Momentum is conserved. Find the velocity of the pellet block system right after the collision. We have a perfect inelastic collision with momentum conserved. That's from the previous slide. So we put in our initial momenta of the pellet and the block. And then on the right side, we have the momentum of each one of them. And that little prime means it's after the collision. Now, what is the velocity of the pellet and block? They're the same because they're stuck together. So we replace each velocity on the right side with pellet PB, pellet block system. And what can we do next? We can factor out the m pellet plus m block times the velocity of the pellet block. Then on our next step, we lost the term on the left side. Why? Because the block was at rest. That term is 0. Finally, we divide through by the mass of the pellet, and this will be our equation to solve. Now, if you get this far, this should get you 90% of the credit on any sort of test or quiz question, okay? Hopefully your teacher does that. I know I would. So here's our equation for the velocity of the pellet block system after the pellet here strikes the block, becomes embedded, and starts moving. And like I said previously, that's the key part of this problem. Now you put the numbers in, go through the math, and you get the velocity of the pellet block system is 1.43 meters per second. Now we'd like to find the kinetic energy of the system right after the collision. Well, we found the velocity on the previous slide right here, and we know the mass. Okay, so here's our mass. It's the mass of the pellet plus the mass of the block times the velocity of the pellet block system, the initial velocity once the collision happens, and make sure you square it. Put the numbers in, and we get a kinetic energy of 1.43 joules. What is the gravitational potential energy of our pellet block system when it reaches its maximum height h? After the pellet strikes the block, it tries to push it to the right? It's got a force going that way. But the strings attached to the block, see the little strings here? They will exert a tension force that also pulls it up, resulting in a circular motion. Okay, so what we have here looks very much like a pendulum, simple pendulum. The system will keep moving until it reaches a maximum height h, and what happens at the maximum height? It has a velocity of 0, and then it starts falling down again. Very much like a projectile motion problem where you shoot one of those toy rockets up in the air. At the top of its trajectory, the velocity is 0, then it comes down, and that gives you the maximum height. Same thing here. There are no external forces here, so that's telling us we can use conservation of energy. The force that the pellet exerts on the block is canceled out by the force that the block exerts on the pellet. It's internal to the system. That's Newton's third law. So we're not going to worry about that. We're going to go ahead and use conservation of energy now. And to really make our point, okay, there's no external net force, so no work is being done. No external work is being done on the pellet block system. So the work is equal to our 0 force times the height. Work is 0. Work energy equation, initial energy plus work equals final energy. Work is 0. So the initial energy is the final energy. I know we did this last unit with the energy stuff, but it's good to review it. Energy is conserved. Here's our conservation of energy equation. And the two things we're worrying about here are kinetic energy and GPE. We don't have any elastic potential energy because there's no rubber bands or springs. So initially, we're going to set this bottom point where the collision happens. That'll be where GPE is equal to 0. We'll say that's we'll say the height there is 0. So our initial energy is all kinetic. Then our final energy, we already said the velocity will be 0 at the max height because then it'll start falling down again. Gravity will pull it down once its velocity is 0. And yes, gravity was pulling it down the whole way, but it was still moving up on the first part of trajectory. And then it starts moving down again once it reaches the peak. So our final energy will be all GPE. So initial kinetic energy is equal to the final gravitational potential energy. Don't even have to do any math here, okay? Because the GPE at the maximum height is equal to the KE of the system at the bottom, right after the collision. So GPE is KE. Gravitational potential energy is 1.43 joules. Find the maximum height of the pellet block system. Well, the first part of this problem, we use conservation of momentum to find the initial velocity of the pellet block system. And we were using kinetic energy down there. Kinetic energy was not conserved. Why? Because it is not an elastic collision. So we couldn't use conservation of energy. Now, we're going to use conservation of energy, though, to find the maximum height attained by the system. So two-step problem. Momentum conservation first, energy second. So as found in part E, we set the KE of the system right after the collision equal to the GPE at the maximum height. But even though we found the value, what was it, 1.43 joules, don't use that now, and I'll show you why in the next slide. Solve the equation algebraically, and you'll find that we can eliminate the mass of the system, and this will tend to give us a more precise answer. We won't be rounding off as much. So here we go. All right, we did this step earlier on part E. Now we're going to substitute the value in for kinetic energy. And notice the subscripts here. It's the pellet block system. And that's going to equal the mass of the pellet block system times GH, right? KE equals GPE. Look what happens to the mass. And the value here is not just number crunching. It shows you the physics behind it. The mass of this system does not matter. So we have 1/2 VPB squared equals GH. We're solving for H. So what do we do here? Oh, we just switch the sides around, divide through by G, and we get here's our height. Look how clean that is. That's nice. No mass there. Very straightforward equation. And finally, we plug in our numerical values. Okay, so there's the velocity we found earlier, and make sure you square it. Common mistake to miss that. Divide it by 2 times G, and we get a height of 0.104 meters, which is what? 10.4 centimeters.